Hey everybody, we're here for the week 6 group problem. And so I've got numbers 1 and 2. And then over here we've got Josh. Yo. And Jacob.
Hello.
A little bit more. There we go. Keep your full face. Don't want half face. So for the very first one, we need to find out the frequency of the recessive D allele in the population. And we know that 1 out of 150,000 people are affected. And so the easiest way to do that is just solve for Q, because we know since it's a autosomal recessive that 1 in 150,000 is the Q squared value. And so if we just take the square root of 1 over 150,000, we get 0.0026 as our Q value. And then from there, we can find out the frequency of the D allele as well. And so Q plus P equals 1. So to solve for P, you can just do 1 minus 0.0026, and that gives you 0.9974. And then for part C, we need to find out what it is for the homozygous dominant genotype. And for that, we take the 0.9974 that we found in the last one and simply square it. Then for the last one, the homozygous, we take the middle section of the equation and just have 2 times 0.0026 times 0.9974. And so, okay, for the fill in the blanks, the first blank is Q, second blank is 2PQ, the third blank in part B is P, and part C it is Q, part D it is Q, part E it is P, part F it is sickle cell anemia, part G is monomorphic, part H is, I don't know, Dean's Demis, however you pronounce that. And then the last one in part I is the major histocompatibility complex, or MHC. On to Josh.
All right. They'll see. It's good enough. Inside joke.
We're just cracking jokes here.
The Glacius
Having
divide.
fun with
Glacius
genetics.
eyes.
The Glacius divide.
Yeah. It's just like our fruit fly friends. So, number 3, we have Marfan syndrome, which is an autosomal dominant disorder. For the purpose of this problem, to assume that Marfan syndrome affects 1 in 6,000 individuals. What's the frequency? So we divide those that do not have Marfan syndrome because it's dominant disorder. So 5,999 divided by 6,000, and that would be Q squared. And then we square root it to get the frequency without Marfan, which is 0.99992. And then B, what is the frequency of the Marfan syndrome allele in the human population? And we take we take P, and we have 1 minus Q, and that equals 0.00008. And C, what is the frequency of heterozygous individuals in the population? And that would be 2PQ. So we just take those numbers, multiply them together, and you should get 0.00016. And then D, out of the population of 5 million people, how many heterozygous zygotes are expected? And that we just multiply the frequency by 5 million, and we get 833. All right, on to number 4. So we have Jeffrey Minton and his colleagues, and they found these genotypes. So we determine the allele frequencies. We get R to the 3rd, and we times 11, which is the homozygous recessive, by 2, because we have 2 alleles in each person, and then we add 44 because that is how many are in the heterozygotes. And then we divide it by 380, and we get 0.1737. And then we can just take that value and subtract it from 1 and get 0.8263 for our squared value. Okay, question B, use the chi-squared test. So our null hypothesis is the Hardy-Weinberg equilibrium is kept in the population. We take the p squared plus 2pq plus q squared equation, and we plug those numbers in that we just got in A, and you'll get 3 different values. You take those values and you multiply them by the, by 190, and you should get the expected values. Then you do the chi-squared formula, and you put in each of the observed and expected values, and you should get, for our chi-squared value, 7.0088. And then because this value is greater than 0.05, our degrees of freedom is 3 minus 1, so we get 2 there. And since our value is greater than 0.05, we fail to reject the null hypothesis. And now on to Jacob.
Hello, I will be doing number 5. And for the first question, they're asking for the frequency of some dogs. We have the CHCH, CBC, and CC. And so we're just going to be taking the probabilities and taking the product of them. And so you're going to have CH, and you multiply that 0.37 squared, and you get 0.1369. If you take CB and C, you are going to be taking the product of 0.25 and 0.15 to get 0.0375. And finally, a double CC would be 0.15 squared, which is 0.0225. Among a population of 2,000 dogs, how many would you expect to have the pale gray genotype, yet be heterozygous? So because of this, you would require to have a CB and a C. There are no other genes that would allow this to happen. So you take the probabilities of both, and then you multiply by 2,000. So 0.25 multiplied by 0.15 times 2,000 is 75. Along with the population of 5,000 dogs, what would you expect if you had a white coat, dark eyes phenotype, and yet be heterozygous? You take the 2 different probabilities that you have, which is 0.15, which is the C, and the 0.23. And you're going to add that to the 0.25 and 0.23 because you're taking these 2 different kinds, which will be the product value, and then you're going to be adding them together for the summation value, and that will be 460 when you multiply that probability by 5,000. Lastly, you're going to take 15,000 dogs. How many would you expect to have a CH, CB, or CC genotype? And with that, you are going to be taking the CC genotype, which is, we've already discovered the value of 0.0225, and then you're going to be adding that to the value of a CH CB dog, which is 0.37 multiplied by 0.25, and then taking that whole probability and multiplying by 15,000 with a approximate sum, or a actual sum of 1,725. And those are the answers A through D for number 5. Thank you. Have a great day.